dear members of the committee, dear colleagues, friends and family. I hope everybody can hear me, because today I will explain you a story about light. More specifically, I will demonstrate you that light perceives reality different than we do. Light lives in a so-called electromagnetic reality. And this reality can be significantly different from the physical reality that we perceive. Moreover, I will show you that recent advances in nanotechnology allow us to transform this electromagnetic reality, hence my title. Now, before I do so, I think I can introduce you first to one of the most celebrated examples of this technique, which is the possibility to make something invisible. Indeed, invisibility is a subject that has fascinated people for over millennia. We can date it back into the mythology in the work of Plato, where it is mentioned in the legend of the Ring of Ginis. But also more recently, invisibility is a key ingredient in many novels and movies. Of course, we all know the novel written by H.G. Wells, The Invisible Man, but also more recently, the series of the Harry Potter movies and books. Now, in my opinion, one of the reasons why invisibility fascinates us so much is because it confronts us with the fact that electromagnetic reality is different from the physical reality. The saying goes, seeing is believing, but as I hope to demonstrate to you today, seeing is not necessarily believing. Now, before I can explain you how invisibility works, I think I need to introduce you to the fact how visibility works. So, what is the process of vision? So let us therefore consider this image of a bowler hat on the background of a blue sky. In order for us to see this bowler hat, we obviously first need a light source. In this case, we can take the sun, for instance. Now, this sun is illuminating the bowler hat, and we can depict the energy carried by the light waves by these yellow arrows shown over here. I will refer to them as the light rays. Now, when these light rays hit upon the bowler hat, they will be scattered and reflected in all possible directions. It is important to note that all the information about the image of this bowler hat is contained within these scattered light rays. So if we position somewhere an observer, for instance here in the leftmost corner, and he sees some of these light rays impinging on his eye, then he will be able, or at least his brain will be able, to reconstruct the image of the bowler hat. So I already see some of you thinking to make something invisible is not that difficult. We just need to make sure that none of the light rays can reflect upon this image. And indeed, this is not a very bad idea for those of you who already had the idea. This is not a bad idea because this is actually the technology that is underlying the stealth invisibility of stealth airplanes. And this is allowing them to become invisible for radar detection. However, if we would position ourselves in the position of Einstein, as I would like to prefer to do for myself, then we see that, as a matter of fact, he would see a black dot somewhere in the sky. And this is a result of the fact that he doesn't see the light rays that are coming towards him. He doesn't see the sun and the blue sky. So clearly, the bowler hat isn't invisible if we reduce the reflections of the bowler hat. To make something truly invisible, we need to achieve two main goals. First of all, we need to eliminate the reflections of the bowler hat. But secondly, and this is way more difficult, we need to make sure that all the light rays are bent around the bowler hat, and that they proceed as if they would have proceed their journey as if they would have just traveled across the bowler hat. In this case, Einstein will perceive an image of the sun and the blue sky, and he will not see the bowler hat, although the bowler hat really is there. Now, I can assure you, to make those light rays bend around a certain image or around a certain object, that's a very difficult task to do. And it's actually impossible within the traditional optical design techniques. Because in the traditional optical design techniques, people are using prisms and lenses and mirrors to make some optical component. However, a few years ago, in 2006, two professors from the United Kingdom, Professor John Pendry and Professor Ulf Leonard, independently discovered that we have some kind of strange thing with light going on. I will go deeper into the details of this. We have a very strange thing, and because of this reason, we can make components that bend these light rays around a certain object quite elegantly. And the underlying reason is actually related to the fact that light is indeed living in an electromagnetic reality. So let me start by going deeper into the physics of this story and discuss with you the first keyword of my title, the so-called electromagnetic reality. The first one to perhaps mention a concept related to electromagnetic reality was Pierre de Fermat. You can see already quite some centuries ago. He was actually a French lawyer from the Parliament of Toulouse, and well, after his hours, he was also a hobbyist in mathematics and physics. Now, so many years later, we only remember his hobbies, but he actually just did it as a hobby. Now, in those days, when you had a principle that you formulated, you could give your own name to those principles. So he stated the so-called principle of Fermat. And the principle of Fermat states that when light is traveling from one point in space to another point in space, it will choose the path that minimizes the overall optical distance. And this is a quite strange principle if you think of it. So it will not take necessarily the shortest path between 2 points, but it will take the shortest optical path. And hence he also defined a so-called optical distance. And an optical distance, well, that's actually defined as the physical distance times the so-called index of refraction. Now here I also define the concept of an index of refraction. And what is an index of refraction? Well, it's a material property. You can associate it to any possible materials here on Earth or anywhere. It's something like charge or mass, although not as fundamental. And some of you might remember an index of refraction from the courses where you saw Snell's law, which is actually relating the refracted light to the incident light at the interface between two media with a different refractive index. But there's actually something more peculiar going on in media with an inhomogeneous refractive index profile. So in media, where the refractive index is evolving as a function of space. And there is a very, very famous example of such a medium, and that is actually happening across above the hot sand in the desert. It's actually also happening on a very warm, sunny day in the summer here above the streets, where the air is less dense close to the street or close to the sand, and then high up in the air. And given the fact that a refractive index is proportional to the density of air, we also know that the refractive index will be lower close to the ground than high up in the air. Now, when a light ray is emanating from this palm tree over here towards this unfortunate observer on the camel, it will not take this straight path necessarily, but it can also take this path shown over here, glazing past the desert surface. And this is because of the fact that the refractive index is lower over here than here. Now, this is actually the underlying physical mechanism why we also perceive a lot of these illusions or these mirages as shown over here. Now, the first thing that I would want to ask you to keep in mind is that light rays can follow curved trajectories when they are traveling through media with an inhomogeneous refractive index profile. So when you have a medium with a refractive index that varies as a function of space. It's as easy as that. Now, we will connect it with light propagation in a completely different context, the context of general relativity. Now, this is not an easy story to tell you, but let me give it a try. The fact is that about 100 years ago, Einstein generalized the law of gravitation by stating that there is actually no such thing as a gravitational force. The only thing that happens is, when you have large masses or energy, they will curve space-time around them. So the coordinate system of space-time is curved by the presence of large masses, as you can see visualized over here. So you have a large planet, and it curves the coordinate around it. Now, a light ray that is coming from a distant star towards us will follow these curved coordinates, and therefore it will follow a curved path. Now, if we position ourselves over here, for instance, at our planet, and we see a light ray coming from a certain location, we will think it will come from here because we think that light rays follow a straight path. But in reality, the star is located over here. So the thing I want you to remember on this slide is that light rays can also take curved trajectories when you have the context of general relativity, when you have the context of a curved coordinate system. Now, the thing is, actually, a few years ago, the two professors that I already mentioned previously, Professor John Pendry and Professor Ulf Leonard, they noticed and they realized that the equivalence between the two different pictures that I just showed you in these two slides goes deeper than just a qualitative picture that I just showed you. So for those of you that came to see some hardcore mathematics here today, and I know you're out there, I inserted this slide over here. For those of you who didn't come to see mathematics, I can assure you this is the only one. But I think it's actually quite interesting to look at this slide. What I'm showing on this slide are Maxwell's equations. And Maxwell's equations are actually one of the most fundamental equations we have in classical physics, because they describe how light actually how electric and magnetic fields, but light is an electromagnetic field, how electric and magnetic fields are propagating through space and time. So you can see over here an electric field and a magnetic field. Now here on the left-hand side, I'm writing down Maxwell's equations in the context of general relativity. So I wrote them down on a background of a curved coordinate system. And the curvature of this coordinate system is encoded by this mathematical beast over here, which is a metric tensor that defines how much the coordinates are curved. Now on the right-hand side, I'm writing down Maxwell's equation in a simple straight Cartesian coordinate system, so no curvature over there, but I'm including specific material components, a permeability and a permittivity. It's enough for you to understand that these are related to the refractive index of a certain material. Now, these two professors noticed that when you have a closer look at these two sets of equations, that they are completely equivalent when we assume the following equivalence relation that relates the permittivity and the permeability, read the material components of a certain specific material, to the curvature in outer space. And this is actually a quite powerful result, because this allows us to go back and forth between a material view and a curvature view. And to demonstrate you how this works, I think I can go through this slide over here. So this is actually how we can use this equivalence, this bridge between a curvature and a material in real-life applications. So what one usually does, and what I also did in my work, is to start by looking at the path of a light ray, and we look at the path of a light ray in an empty space, and we express it on a normal, straight Cartesian coordinate system. So this is actually the situation I have over here. Empty space, okay, there are a few people here, but around me, it's empty space and a straight Cartesian coordinate system. So when I shine with my pointer over here, it's clear that this light ray is following a straight path. That's actually the reason why pointers are so convenient to use. This is the red line shown over here. Now in the second step, we will express this same physical phenomenon on a different coordinate system. So we're just going to stretch and deform and bend the coordinates in order for our light ray to follow a quite exotic path. Now this is something, of course, that you cannot do in reality. You cannot stretch the coordinates in such a way that you want it. But what we can do is materialize a certain coordinate transformation inside a specific material, using the bridge that was shown in the previous slide, that relates the permittivity and the permeability to a curvature tensor. And this is the way that transformation optics, because the underlying technique that I'm describing here is transformation optics, this is the way how transformation optics introduced in the last decade several novel applications. And to demonstrate you how it works, I think I can go back to the initial example of invisibility. As I mentioned you, to make something invisible in the traditional optical design techniques is almost impossible. Whereas using these coordinate stretching, it's easy as anything, because what we simply need to do is curve our coordinates around an inner region, such that in between these two blue circles, we are opening up a certain circle, such that all coordinates are stretched out of each other. And then, of course, the red line here will follow these coordinates and will be bent around a certain region. In the next step, we can then use the equivalence relation to calculate the material parameters that are required to materialize this in our physical reality, such that anything positioned inside this physical space will turn invisible for external observers. And this is then graphically shown here in this rightmost picture. I do like three-dimensional figures, so I made one, where we have a cloak, and the blue lines represent the light rays, and these are bent around the dark green region, which therefore turns invisible. Now, of course, transformation optics only tells us what kind of material parameters we need to realize. It doesn't tell us what materials we can use. So it doesn't tell us, well, now use glass or use wood or use metals. So to materialize these components, to really make them in reality, unfortunately we found that there are no such materials. So we cannot simply go and look in the woods for some specific material that has these components. So this brings me directly to the second keyword of my title, which is called metamaterials. And those of you who have some notions of Greek will know that meta means beyond. So in a certain sense, these are materials that go beyond the traditional materials. And although the research field is quite recent of metamaterials, it started in 2000, actually the first notions of metamaterials can be traced back about to the 4th century. because the Romans actually also had some kind of metamaterials. This is so-called the famous Lycurgus cup, and there's something very specific with this cup, because it contains glass that has a different color depending on where you put your light source. If you put your light source in the audience, then you will see green light. If you put your light source behind the screen, then the light would become red. So that's a very specific thing, and that's something you cannot do with traditional light or with traditional glass. And to make such a glass, the Romans were actually making composite materials. So they were making man-made composite materials in which they were including small metallic alloys, inclusions, inside the glass. So here you can see, for instance, such a small metallic inclusion, which can be gold or silver, and you make it really in very, very small amounts. You put it inside the glass. And to give you an idea, these are indeed very, very small amounts, because this is 50 nanometers. Now, I can imagine that most of you are not using nanometers as an everyday tool to measure something. So to give you an idea, our human hair is growing at 5 nanometers per second. So our hair already grew more than 100 nanometers in this presentation only. So this is a really, really small dimension, of course. Now, more modern metamaterials don't look like the Lycurgus cup. Modern materials are artificial materials where we are trying to make electromagnetic responses that cannot be found in nature. And to demonstrate you how we do this, I think it's most instructive to first consider a traditional material. Here on the left-hand side, I'm showing you a traditional material like glass, for instance. Now, the electromagnetic response, read the index of refraction of glass, is entirely determined by the individual atoms or molecules. So when you illuminate such a material with light, all the individual atoms will start to resonate, and they will become small antennas and re-emit the light, and as such, the material starts to play a macroscopic role. Now, for a metamaterial, we're going to change the functionality of those little individual atoms by small metallic inclusions that we design ourselves. So we make it so small that from the perspective of light, from the wavelength of light, these metallic inclusions play the same role as these atoms. And in this way, we can design macroscopic media, so from the perspective of the wavelength of light or larger, with a refractive index that cannot be found in nature. For instance, researchers have been able to demonstrate that you can make a metamaterial with a negative index of refraction. So the combination of these two concepts, the geometrical intuition of transformation optics, in combination with the nanotechnology of metamaterials, allows us to make things that simply cannot be found in nature. And to demonstrate this to you, I'm showing you here the first real-life invisibility cloak. Now, I know that there are some critical spirits in this audience, and then obviously you might think that this is clearly not an invisibility cloak, because we can see the cloak, and we can see what is inside the cloak. So before you start to accuse me of saying some lies to you, I want to mention that this cloak is actually working at wavelengths of approximately 3 centimeters. So those are not the optical wavelengths of light that we can see, but those are the wavelengths of light that, for instance, work for our cell phones. So if you put a cell phone inside this cloak, the cell phone will be cloaked or will become invisible for other cell phones. Okay, you're not impressed, but I can assure you, I can assure you that in recent years, also at higher frequencies, invisibility cloaks have been made. Now, this is actually the period where I started my research, so many years ago, because this is actually the main success of transformation optics. When I started, we had an invisibility cloak and several other applications, but they were all aiming at distorting a certain ray propagation or modulating a certain beam modulation. So the natural question that we were posing ourselves was actually whether we can extend the language of transformation optics. Can we understand novel physical phenomena, or can we design novel optical devices beyond the traditional ray picture that I showed you just before? And during my PhD, I actually formulated an answer to this question. And I think I formulated an answer to this question that it's 6 times yes. So we can indeed extend the scope of transformation optics beyond the traditional applications. And although I do not have the possibility to explain here everything to you, I would like to show you in the next, well, 15 to 20 minutes, the 3 first themes that I did during my PhD. So the possibility to confine light below the diffraction limit, the possibility to enhance optical gradient forces, and of course also the possibility to convert the color of light. So let me start off with the first theme of our research. The first theme of our research is the investigation on whether we can confine light in small resonators using these geometrical principles of transformation optics. And the confinement of light is an extraordinary important aspect in current information and communication technology systems. Because, as you might know, whenever we're doing a Google search or whenever we're Skyping with one of our advisors over the internet, all of the information is converted into the optical domain. And this is actually sent all over the world through some optical fibers, as you can see over here. Now, it is actually much more logical to keep the information in the optical domain and then manipulate these signals in the optical domain. And one key ingredient to manipulate systems is actually the ability to confine and store your light for a certain amount in time. And nowadays, researchers are actually using so-called microresonators to do this trick. And a microresonator is shown over here. Notice the dimensions of a few tens of micrometers. And a micrometer, by the way, is approximately the thickness of our hair, so it is still very small, of course. And inside such a microresonator, we can confine light through total internal reflection at the boundaries of the system. Now, I can imagine that most of you do not know what total internal reflection is, so I brought here with me a little setup that hopefully will demonstrate the thing. So I have a laser pointer here, and I'm going to shine it through this glass. And as you can see, normally, the glass will follow, the light will follow the bending of the glass, because it totally internally reflects on the boundaries of the system. So this is essentially a microresonator operates on the same principle. It actually confines light by letting it reflect upon the boundaries. And this actually works pretty well. There is unfortunately a very big problem related to these microresonators. And this problem is shown over here. Unfortunately, we can only confine light within these microresonators at specific resonance wavelengths. And those of you who ever played a musical instrument will know what a resonance wavelength means. And those of you who didn't, I brought here a small guitar, so you can immediately see it. So if I want to confine a certain wave on a guitar string, which I do like this, then you will hear a tone that is related to the length of this guitar string. And actually, the wavelength that you hear approximately equals the length of this string. So if I make this string shorter, you will hear a louder, a higher tone. And this is actually the same case with the microresonators. If you want to confine your light inside a microresonator, you at least need to make sure that the microresonator is larger than the wavelength of light. And the wavelength of light is approximately 1 micrometer. So you cannot make these microresonators smaller than 1 micrometer, approximately. And this has quite some severe consequences, and it is shown here in this comparison between an electrical circuit and an optical circuit of the same dimensions. These are approximately a few micrometer. On the electrical circuit, you can easily include a few millions of components, because they are not limited by this previous limitation. Whereas the optical circuit, because of this limitation, can only contain a few hundreds of components. So you have a severe, miniaturization limitation related to these microresonators. So in our work, we actually wondered whether we can use the geometrical formalism of transformation optics to design novel type of microresonators. Because smaller resonators, they would not only be faster, but they would also require a lower amount of energy. And to do this, we actually returned to the initial example of the invisibility cloak. It's shown over here. So here again, you can see the coordinate lines that are bent around a certain inner region. But you can actually also look at an invisibility cloak from a different perspective. You could say that an invisibility cloak is prohibiting light from entering a certain region. And what we want to do with a microresonator is doing the exact opposite. We want to make sure that no light can escape a certain region. Or to put it in other words, we want to make sure that the outside world becomes invisible for the inside world. And so therefore we designed this microresonator based on this coordinate transformation. And after some tedious calculations, which I won't show you here today, we found that indeed such a microresonator enables us to confine light below the so-called diffraction limit. And this is well understood by looking at this picture over here, where we're looking at the density profile. So we're looking at the electric field distribution inside a traditional microresonator, and we can compare it with the electric field distribution inside a metamaterial resonator that we designed. And as you can see immediately, although the dimensions of such a microresonator are fundamentally limited by this diffraction limit, we can easily circumvent it using these transformation optical designs of metamaterial resonators. So this is actually the first example in which I hope to have demonstrated that the combined approach of transformation optics and metamaterials allows to question and even circumvent existing taboos in electromagnetism. But this is not the end of the story. Indeed, we also apply transformation optics to the enhancement of optical gradient forces. Now, the context of this work is given by the fact that researchers are in recent years trying to find means of manipulating devices on the smallest nanoscales. So we actually want to have the ability to make very small motors or machinery, as shown over here, and then make them move, because that would increase our ability to manipulate light even further. And as you can see here, 3 examples. Now, the natural question that then arises is, how can we make those things move? Because here again, notice the scales. This is the scale of a few hundreds of our hair thicknesses. This is really, really small. So clearly, a traditional screwdriver won't help us to make these things work. And the answer to this question was actually provided a few years ago by several groups all around the world that demonstrated that you have such a thing like optical gradient forces. Now, to understand these forces, you can either look at these figures, which are experimentally taken photographs, but I think these sketches are more suitable. So what researchers demonstrated was that if you have 2 waveguides, and I made a high-tech example of this, so if you have 2 waveguides, and light is propagating through these waveguides in this direction, and you position them very close to each other, then these waveguides will start to attract or repel each other. That's a physical phenomenon that has been demonstrated. Unfortunately, there's a problem. And the problem is seen on this graph over here, where we're looking at the optical force as a function of the separation distance between both waveguides. And as you can see, although the forces can be relatively large at very small separation distances, whenever the waveguides are getting at larger separation distances, the forces become very, very small, because as you see here, this is a logarithmic scale, so the forces decay quite quickly. So to solve this problem, we again considered the geometrical formalism of transformation optics. And to do this, I can return back to my example over here, we actually wondered what would happen if we would have a coordinate transformation that folds the coordinates back on themselves. So to create the illusion for light that the waveguides are closer to each other in the electromagnetic space than they are in the physical space. So this is a type of coordinate transformation that we wanted to implement. And to implement such a coordinate transformation, we needed here again a specific metamaterial. And this is shown on this slide over here, where we're looking at the 2 traditional waveguides here in the light blue, and then we attach to it a metamaterial cladding, which contains of an array of small metallic inclusions in a silicon background. I think I can best proceed to the final result that we obtained over here. I won't bother you with all the finest details of this result, but here again we're looking at the optical force as a function of the gap distance, and I want you to compare the black line, which corresponds to the traditional state-of-the-art without metamaterials, with, for instance, the red diamond line, not by chance the best line that we obtained. And you can see that indeed, for large separation distances, we can enhance the optical gradient forces by more than 2 orders of magnitude. And this really enables us to have large optical force and therefore also enable all optical device actuation at realistic separation distances. The last theme that I would like to discuss with you is probably even more exotic. It is related to the fact that it is extremely difficult to change the frequency of light. And we all know this. For instance, I have a green pointer over here, and I might do quite some things with it. I might send it through the waveguide, I might let it reflect, or I might do most of the things I want to do with it. It will always stay green light. It's very difficult to change this light. And this is actually very much in contrast with the fact that light is being frequency shifted all the time in our universe. Our universe is one very big frequency shifter. And this is related to the fact that our universe is expanding as a function of time. And I know that it's quite difficult to understand such a thing, so cosmologists usually refer to such a metaphor of a balloon. We have to imagine that our universe, our galaxies, our planets, they're all living on the surface of a certain balloon. And that this balloon is being inflated as a function of time. So universes that were quite close to each other in the beginning are now very much separated. Now, of course, what we could do is draw now a certain wave on this universe, on this balloon. And of course, when this balloon is stretched, you will see that this wave is also stretched. So the wavelength is expanding as a function of time. And this physical phenomenon is referred to as the cosmological redshift, because if you have a longer wavelength, you will have a shorter frequency and therefore also redder light. And this cosmological redshift is actually widely used in cosmological observations, because if we observe here on Earth light that is emitted by a distant star, and we compare the frequency of this light to the frequency at which it was emitted, we can find how long this light was traveling, and hence where the light is coming from. And in this way we can make a map of our universe, the so-called W map, that indicates us where everything is situated. Now the real question that we were posing ourselves is whether we can transpose this physical phenomenon of an expanding universe, a universe that is growing as a function of time, inside a small metamaterial. Because as a matter of fact, the stretching of the stretching of the universe is similar to a stretching of coordinates. And therefore, we applied the equivalence relations of transformation optics and calculated what kind of permittivity and permeability, read what kind of refractive index is required to mimic such a growing universe. And we did find that if you eliminate such a metamaterial, which is a metamaterial whose refractive index is growing as a function of time, if you illuminate such a metamaterial with a blue plane monochromatic wave, then at the backhand side of this slide, of this component, you will have light at a different frequency, whose frequency is exactly frequency shifted according to the cosmological redshift formula. So this shows us two main things. The first thing is that we can indeed reproduce cosmological effects inside tiny materials. And secondly, it offers us a novel approach to shift frequencies of optical signals, which is relatively difficult. Furthermore, we actually had some numerical simulations. I won't go into the details of these graphs, but here we're actually comparing an incident signal, an incident pulse, and the transmitted pulse in 4 different cases. And we found that indeed we can retrieve a 10%, 30%, 50%, and even 70% frequency shift, something which is extremely possible, extremely difficult with the contemporary frequency shifting device. Now, I think these results unambiguously show that it is indeed possible to convert the frequency shifting mechanism of our universe that happens on the largest scales of our universe inside materials that are built and that are made on the smallest scales that we can achieve. So let me now proceed to some very general conclusions. First of all, I hope to have demonstrated to you that we shouldn't trust light too much. Light is living in a different reality from the one that we are living in. And this creates several optical illusions, but it can also be used in our benefit. I have demonstrated you that we can transform the electromagnetic reality in the way that we want it. We can mold the flow of light up to unprecedented degree. For instance, by the development of metamaterials that can be combined inside an invisibility cloak. And I hope to have demonstrated to you that the combined approach of transformation optics in combination with metamaterials allows us to confine light far below the diffraction limit. It also allows us to enhance optical gradient forces, which would enable all optical device actuation. And last but not least, I hope to have demonstrated to you that the frequency of optical pulses can be shifted inside a medium that is implementing an analog of the Robertson-Walker metric. Now, I want to go out with a few perspectives, because I think this is quite important. The first perspective that I would like to say is that it is necessary to, it's very important to close the gap between the optimism of transformation optics and the realism of metamaterials. Because nowadays, the framework of transformation optics is giving us material components, like refractive indices, that are still too optimistic in relationship to the metamaterials that we can make. In the other way, it would also be nice if we could develop metamaterials that are evolving as a function of time, because this would enable us to achieve the frequency shifting effect that I demonstrated you just previously. I'm also quite excited about the development of two-dimensional transformation optics, in which we can mold the flow of light at the interface between two surfaces. And finally, I think it's also quite interesting, also for the multidisciplinary background of this audience, to see that the general concepts of transformation optics, these geometrical tools, are readily diffusing to other paradigms in physics. Because as a matter of fact, if you ask me, the first real-life invisibility cloak with practical applications that will exist here on Earth will not be one that operates at visible frequencies. It won't even be one that operates for electromagnetic waves. It has been shown that invisibility cloaking can also be transposed for tsunami cloaking. This is something that researchers are now working on, and there are even already quite some plans going in the direction of making such a thing, where you have water waves in the sea. So here you have the sea, here you have an island, and suppose that you would have a tsunami coming towards this island, then also this wave equation can be transformed, and you can, by including specific components in your sea, concrete pillars, you can deviate the tsunami wave around the island, which is of course not very nice for the islands which are lying behind this island, but that's just how it goes, I guess. The same is true for earthquake cloaking. Very recently, actually 2 months ago, several researchers demonstrated that you can cloak certain buildings for earthquakes. Here as well, you can have seismic waves that are coming towards this very fancy building over here, and by incorporating specific materials in the ground surrounding this building, you can deviate the earthquake around the building. Finally, I also want to mention the acoustic cloaking, where you can also apply the same principles to make something invisible for sound waves, something that might be interesting for people living close to an airport. And of course, last but not least, there is the possibility of thermal cloaking. When you have a very high heat source and you want to shield this here from a certain temperature, then you can structure a certain material around this medium to make the heat flow go around this certain region. In any case, if you ask me, these results are just the beginning of a very fascinating field. They're just the tip of the iceberg. And there are probably many more things yet to be discovered in this exciting research field. Such that perhaps one day in the future, this surrealistic painting of Magritte might be considered as a realistic picture. Thank you.